All right, guys, so let me give you the steps in order to solve this problem. And I'm going to do it without making an assumption. Then if you want, you can make your own assumptions afterwards. So just copy this figure, and I will do the same thing on my end. Okay. Okay, so that's basically what we have over here. All right. All right, so you see what I'm writing here. So now I'm able to write there. See if I can make this a little bit more to the left. All right, I'll try to do my best over here. So what do we know over here? I think I forgot to put the radiuses. So this is R, this is 2R, this is M. Okay. So I think on the problem, we said that this will be R, this will be 2R, and then I added, let's say this has a moment of inertia, J sub 1, and this one has a mass and moment of inertia, J sub 2, okay? All right, so I'm just going to do this following the procedure. Then if you want to do some simplifications, it's fine. That would be up to you, all right? So first thing is to do free body diagrams, all right? So one, free body diagram. So we need how many free body diagrams? We're going to need one for the pulley here, one for this pulley, and one for the block. All right, so let's do them. So let's say this will be this center, let's call it O, this one P, so we can make the difference. It will be O, O. Then we need one for the second pulley, and one for the block. Okay, so what would be the forces acting on the first one? We'll have the force of the spring now. So let's say, for now, let's just call it some Kx. You don't know how much it's going to be, so let's call it Kx1, okay? We can simplify, but and then what will you have on the other side? A tension T, okay? If I don't remove the fixed position, I don't need to put the reactions. That's why I don't even provide the mass. What is the motion of this pulley? It's just rotational, no? Okay, so if it's just rotational, the only equation that we need in order to define the motion of this one will be summation of moments. Okay, now this pulley over here, what will you have? So you will have the reciprocal to this one, so it will be T on this side. Then what will you have on that side? Let's say 5K X2. And what else? Here you will have, so this is might be a bit more complicated, it will be mg. All right, but then what do you need to add over here? So maybe we need to change a bit the notation. Let's call this one T1 over here. Forgot we need another one. So T1, and this will be the T2, which is the tension of the rope between this pulley here and the block, no? Yeah. So if I do now this one here, sorry, this will be capital M. Sorry for that, because the mass of this pulley is capital M. So be careful, this is capital M. Now this one will have, we need to be careful with this one because, so we'll have the T2 going down. Then what are we gonna have? We're gonna have the mg, and what else are we gonna have? It doesn't matter if you do it up or down. Let me just do it up, and then you'll have here the 2k x, no? Okay, so on this side, I did all the forces. So let's go back to the first one. This one, this is summation of moment. We have those two forces, and this will be rotating with some J1 alpha. And to save some time, we know this will be alpha 1 if you want. This will be J1 theta double dot 1, no? Because alpha is the second derivative. We can use alpha as well, it doesn't matter. Then this one, the second pulley, what type of motion is going to have? This one is going to move in rotation and translation. Okay, so we'll have some J2 alpha 2 or J2 double theta double dot, so theta double dot 2. And then this will be moving with what? Make it going up with some acceleration, capital M A, which is the same thing as capital M X double dot. And this one here will be moving with an acceleration, lowercase m, A, which will be the same thing as M X double dot. Okay, so any questions so far? This is, I think, sometimes the most difficult part, okay? From now on, it's just to write down an equation. The only thing I'm gonna change, because I like to be traditional with the units, with the units and the reference frame. Oops. This one, I don't like it to be down. So let me make it just go up, okay? Which would be the traditional reference frame. So our traditional reference frame, let's say, will be for me, they will always be going up, okay? So this is the X of t, which is the node we know that is for this block right here. All right. So again, I'm going to give you the steps, but you don't have to do it. So step 1, free body diagram. Step 2, right? I like to call them kinetic, but it's the same thing as saying dynamic equations. All right, so the dynamic equations must come from the figures. Okay? So this pulley over here, what type of motion is it having? Just rotation. So the only equation we need to take for that one will be summation of moments about point O will be equal to, okay, I'm going to write the general equation, I sub O alpha, and you need to specify the direction. Let's call this one alpha 1 because it's different. But in our case, this is the same thing as saying summation of moments about point O, and the moment of inertia of that pulley is J1 theta double dot 1. Yeah? Okay? And this will be our equation. So again, you need to specify the point and the direction and take positive to be counterclockwise. That's the normal notation, no? This will be our equation 1. Okay. Now, for the second pulley, what type of motion is this pulley having? Translation and rotation. So we need to specify both of them, no? Okay. So for the second pulley, you're gonna have to, for the pulley with center P, you're gonna have to define summation of forces equals to MA. Yeah. And summation of moments about point P equal I sub P. Okay, but that one will really become summation of moments about point P equal to J2 theta double dot 2. So this will be equation 2. This will be equation 3. Okay, that you can write, no? So you have 3 equations. And now finally for this one here, for the little block, what type of motion is this one having? Just translation. So the only equation needed is summation of forces equals to MA. So for that block, we're going to do summation of forces. And here, if you want, this will be capital M. If you want, this is the capital M to help, okay? Force is equal to MA. So this will give you summation of forces equal to, mx double dot, and this will be equation 4. So if you want to help you, this equation here is for pulley with the center O. These 2 equations here are for the pulley with the center P, and this one here is for the block, no? Yeah. All right, so now in your head, or you can write it down. In your head, what do you need to do? Okay, it's going to be difficult here because we don't have it, but what would be the unknowns? So at this step, you come here, you say I have 4 equations. It's easier, if you write down the equations, but out of this first figure, how many unknowns are we going to have? Probably T1, no? X1, and let's say alpha 1 would be unknown, no? Yeah? Out of the second figure, what would be unknown? T2, X2, and alpha 2. If I miss something, let me know. And on the third one, basically, you want to put X as an unknown. We need to write everything in function of X. So X will be the unknown we're going to solve for. So maybe we don't need to put it, no? 1, 2, 3, 4, 5, 6. You want to put X or no? Not really part of the unknowns because it's the one we'll be writing the equation. So 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 6. Did I forget anything else? No. All right, so 6. So can you solve? The answer is no. You need to have the same number of equations as unknowns, no? So now, step 3, you need to find the additional equations. You will go to kinematics. So this is the part that you need to come with some knowledge from dynamics. So I'll try to give you the equations. So let me just redo the figure. So this will be P, no, that was O. P. This radius is R to R. Okay. Okay, so let's give name to some points over here. So let's say this will be so let's use, you want to use numbers or letters? So let's call letters. I think it would be easier. A, O, B. So this point and this point is the same, no? Yeah. So can we just say this one will be B prime equal B, whatever you want. Then we have P, and let's call this one C. Okay? I mean, any question on the procedure? I'm not doing the calculation. I'm just giving you all the equations, no? For you to complete. So over here now, what do we need to find? We need to find first a relation between, let's say, the alpha of this pulley, which is on this equation, and the alpha of this one, correct? If you remember from dynamics, how can you find the relation between two different rigid bodies? You need to find the location that they have in common, no? What is the location they have in common over here, those two pulleys? This point here, behavior of this point is going to be the same as this one, no? So what could we do? We could calculate, let's say, the acceleration of point B from point O, and then we could find the acceleration of point B, let's say, from point P, no? And or something like that, and see what happens. We can equate those two equations, and we'll see what happens. All right, so remember here again, this is our X. All right, so from the figure, you can write down what? You can write down the acceleration of point B. If we use the dynamics equation, will be equal to what? The acceleration of O plus alpha 1 cross R of B with respect to O minus omega squared B 1 R square of B with respect to O. Do you recall that equation from dynamics? Have you seen it before? Yes, no? And generally you use for linkage bars. So in this case, point O, you need to have the figure by side. Point O is fixed. So what would be the acceleration of point O? 0, no? Yeah. In this case, this problem, let's say that is initially at rest. So if it's initially at rest, what does that mean? That the system is just going to be accelerating, no? Yep, it's never going to be a constant. So, and here we let the math giving us the directions and the signs. So if you do this cross product, I do the first one with you. RJK 0, 0, alpha 1. You want to do the first to find the relation, and then I'll let you do the other ones. What is the position of B with respect to O? R 0, 0. Yeah? Okay. So this will give you what? Acceleration of B. And if you think about it, the acceleration of B should be in what direction? On the y direction, no? What is the math going to give you? X will be 0, no? And the y will be equal to what? So we'll have R alpha 1. Okay? And this will be, let's say, your equation I. Now we need to be careful with the other one. We can also calculate the acceleration of B from where? From point P, no? Because this point is the same as this one. So here you have what? Acceleration of P plus alpha 2 cross R of B with respect to P minus omega 2 square position of P with respect to P. Okay, that's the only one I'm going to do the calculation with you. Then I'm just going to give you the equations. So again, if the system is initial at rest, this will be 0, no? What would be A sub P? Okay, would be x double dot, no? It's our origin. So really, if you do this one, this should be equal to what? If we do the vector, will be x double dot 0, 0, no? Plus the ijk 0, 0, alpha 2. And what would be the position of B with respect to P? Minus 2R. 0, 0. And sorry again, this x over here, I put it on the x, but really should be on the y, no? So sorry for that, this will be 0. Just because you have the x, I wanted to put it there. It will be there. So this will give you what? So we'll give you that A sub B is equal to x double dot minus 2R alpha 2. Okay, so if I started to square this one, I have to do this one. This will give us equation Roman 2. So this one here specified about the same point, no? Yeah. So we could say equate those two relations, and that will give you what? R alpha 1 equal to x double dot minus 2R alpha 2. Okay, so this gave you a relation between alpha 1 and alpha 2 in function of x double dot, no? Which is what we need to do. So for example, in this one, if you want to rewrite alpha 1, you can say it's equal to, it will be complicated, will be x over r minus 2 alpha 2. Okay? Or vice versa. I don't know how you will have to play with this one. So this will be equation probably 5. All right, and now so let's see, what else can we have? Okay. Now the next thing you need to do, and here I'm just going to give you the equations. We need to find x1, x2. So we have 1, 2, 3. Okay, yeah, we're good. x1 and x2 in function of the other one. So in order to do that, how will you do that? I mean, like we did the other day, you can kind of do it with some logic, but if we needed to do it with equation, I think we discussed that at the end of the other day of the class. So we see what should be the answer. If this one, let's say, moves 1 down, okay, what's going to happen? This one's going to move 1 down. This one's going to move one down. Okay, well, not really, but. And then how much is that one going to move? 2, no? Yeah, okay. Now let me ask you something. And that's where you can make that assumption or not, okay? That's going to leave it up to you. You don't have to, but is this pulley rotating? Or that one is not really rotating, that pulley, when it's moving? Because if this is rotating, this is going counterclockwise, no? Yeah? So then the displacement of this point here should be equal to what? Whatever this is moving, no? Yeah? Plus whatever this is rotating, no? Does that make sense or no? I mean, if you want, let's write it down. What I want to say is that for x1, x2, what do you know? You know that velocity is distance over time. So velocity is distance over time. So if you fix time, you could say that the deformation basically would be proportional to the velocity, no? Yeah, because all this block is going to be moving on the same scale of time. All right, so let's say if you wanted to find the relation between x and let's say this one here or this one, okay? Let me just do this one. So we could write down what? That should be this figure over here. So let's say you write down the equation, velocity of c from point P. What would be the equation? Vp plus omega 1 cross r. Oh, so maybe we don't have to do that assumption. Yeah, maybe, I mean, that's good. C with respect to P. You know what? Let's simplify the problem since we have that equation. So, since we say in the problem that this is initially a rest, okay? So what could we say about omega 1? We say that it was 0. So we could say basically here that Vc basically would be the same thing as Vp, no? And for the one on the other side, which is what we just said, no? We could do the same thing. Velocity of, for this one, what would you have? Vb with respect to P would be what? Vp plus omega 1 cross R of B with respect to P. And because this is 0, initially at rest, this is not really the reason, but what would you have? Vb will be equal to Vp, which these two over here will imply what? That x, how did I call the x on that side? X2 will be equal to x. And this one, you can say that, okay, we don't need that one. This one is not needed, okay, but xp will be equal to x, no? Okay, and now, so you know this velocity here. Now, could you find the velocity at A or B from this point over here? Yes, no? So then you can find what would be the, how do I call that one? X of 1. So let's see, how could we do that one? Probably would be easier if we do it from here, from the center. But this one will give you in function of Okay, let me see for 1 second here. It will be. So I don't know how far I need to go, but basically now, let me just repeat it. You can do the homework with that information. All right, so go ahead and do it. When did I put it due? Today or Thursday? Thursday. Okay, so you have time. Please, guys, follow the procedure and get one equation. If you want to do another simplification, maybe do that J1. It will be easier probably for the J1, say that is equal to, they'll say those two pulleys have the same weight. So let's say this will be M R squared over 2, and J2 will be what? M 2R squared over 2. Okay, because I'm going to tell you right now the way I'm going to do it. I'm going to write down the equations, 1, 2, 3, 4, 5, 6, whatever equations I need in Maple. And I'm going to say at the end, solve for all these variables. Okay? And then I will substitute into, what is the equation you need to substitute at the end, everything? Into this one, no? Yes. I'm recording now.
If we do this assumption that the pulley 2 is not rotating.
So then the J doesn't do anything.
Yeah. So
yeah.
do we need to have that?
No, because this is still going to do something. It's true that we don't have it. Yeah, so I don't know now. If we don't have it this here, then we don't have any. So then you also need to assume that alpha 2 is 0. No? So then this equation here, good question. So that equation here will simplify even more, no? Because you will say that alpha 2 is 0. Okay? I mean, just do it with the assumption or with the other assumption. Okay? And see what you get. All right, to tell the truth, not for this semester, but I was thinking that for another semester, what I'm going to do is I'm going to take this problem, I'm going to put some data, I'm going to ask you, okay, solve it. And use the solution of the solution manual, do your own solution and compare to see really how good the other one is. All right? Because that would be the interesting part, no? It's not like, this is something you need to get used, guys, and that's what I really wanted to do this, is that in engineering, I mean, this is not a very complicated problem, but you see it's already complicated, a little bit complicated. If you give a problem to 10 different engineers, you can get 10 different answers. But that doesn't mean that the 10 different answers are going to be giving completely different results, no? They're all going to give you kind of the same results, depending on what? On the assumption that they are doing in order when they do the modeling, no? Okay? So don't think that when somebody asks you to do a problem, there's one solution. The solution is going to depend on your assumptions. Okay? And the good thing, what experience gives you is to know what is the best assumption. Do we need to do the whole complexity in this problem to get an equation that is accurate? Or maybe assuming that this is not rotating will give you a solution that is 95% as accurate as the one with every single variable, no? Or with the solution of the solution manual doing the equivalent spring is 90% as good as the one of the full solution, no? That's really what would be interesting to find out. All right. So anyway, and now for the homework, we need to move ahead. All right, so on the class notes, if you want, I will put this that we just did. We need to go to page 59. There we go. Forced, damp, vibrations. Okay, so again, the same procedure as the first time. So this time, our figure will be what? We'll have our mass, M attached to a spring, and we have here a damper, a viscous damper. Let's say there is no friction. This is M, K, C. No friction with the surface. No friction here. But this problem, as is shown over here, is what? This is, if we move it here, if we displace this mass and let it go, it's going to vibrate that way back and forth, no? And this will be the free vibration because you just let it go. There's nothing forcing the motion. So what do you think the force term means? The force terms mean now that we're going to have a force over here that will be creating the excitation of the system. Okay, so again, in this case, it will be a lot simpler, but first step would be to do what? Find the equation of motion. In order to find the equation of motion, what do we need to do? Step one, do the figure of the free body diagram. So I go a bit faster here. See, I'm picky about the procedure because the procedure is always going to yield to the solution. One of the forces here will be Kx. What do we know about the force of the damper? You know that the force of the damper is always proportional to the velocity. Okay, for viscous damping. What else do we have? F of t. Then these ones, we don't need them, but let's put them if you want. Mg and the normal force. Okay, what is the inertia effect? This will be just moving on the x direction. So MA will be mx double dot. Well, let's say this will be our x. Okay, if you have any question about the procedure, stop me, okay? What is step two? You write down the kinetic equation or the dynamic equation. So in this case, the system is only moving on the x direction, no? So that's the only one we need. So we're going to do summation in the x direction equal to max. What would that give you? Minus kx minus cx dot plus f of t will be equal to mx double dot. Or this will give us mx double dot plus cx dot plus kx equal f of t. Okay, so here, this is the form that I like to keep it, all right? But let me just rewrite it here, or this could be equal to what? X double dot plus C over M X dot plus K over M X equal to F of T over M. But this will be the same as what? X double dot plus C over M plus what? What is the K over M? is the natural frequency, no? X equal f of Tm. So in this case, you have omega n squared is still, well, without the square is still k over m, which is the natural frequency. Okay? But let's keep this one. All right, so on the previous solution, when we had the free vibration, go back into your notes, what did we do? What was the first step in order to solve now the differential equation of motion? What did we do? Go back. So to find solution to the equation of motion, let us assume the external excitation f of t to be of the form f of t, let's see what I have on the notes, equal to f sub naught e I capital omega t. Okay, well here capital omega is the force frequency. So basically imagine that this is attached to a shaker and you know that the frequency of your shaker is given by omega. Okay? So in that case, the equation of motion becomes what? M x double dot plus c x dot plus kx equal to s sub naught e I omega t. Okay, we still have time. So what did we just say? Steps in order to solve the differential equation, we assume the solution, no? In this case, we say that the easiest form would be to assume the solution to be in function of the force frequency, no? Not the natural frequency. So step one, assume harmonic solution, same as before. So in this case, we can say x of t would be, let's say, an x sub naught E I omega t. You see, it's in function of the force frequency, not anymore the lambda, which is equivalent to the omega sub n. So now that you assume this, what can you do? What would be x dot? X dot would be equal to I omega x sub naught E I omega t. And x double dot will be equal to what? I squared will be equal to -1. So we have minus omega squared x sub naught E I omega t. Okay, guys, it's important that you know the procedure. So what is step 2? We substitute these ones into the equation of motion, no? All right, so substitute into equation of motion. This is going to give us what? So it's going to give us, let's write down mx double dot plus cx dot plus kx equal to f sub naught E I omega t. So this will give us, gonna simplify right away. So it will give us x sub naught E I omega t for all the terms because it's common. Factor of what? So the first one will give us minus m lambda squared. The second one will give us plus I c omega. And the last one will be, so x will be plus k. Oh, sorry, you see, I did my mistake here. I was just thinking free vibration. This should be equal to what? F naught I omega t. So why is this so good? What can we do now? We can cancel out, no? Okay, that's the whole reason why we assume the solution in function to be in function of the force frequency, so they can cancel out. So now from this is our assumed solution. The capital omega is known because it's the frequency of the shaker. Okay, so it's known. So what is really unknown over here? The x sub naught, no? Okay, the f sub naught can know. This is an input from the machine. So we can solve for x sub naught from here. So we find that x sub naught will be equal to f sub naught divided by, I'm going to write it a bit differently, k minus m omega squared, capital omega squared plus I c omega. Okay, I'm going to write this a little bit differently. I'm going to say that this is equal to S sub naught times a function h of capital omega. All right, and obviously on the next page, the only thing I'm going to write is where H capital omega is equal to what? 1 divided by K minus M omega squared plus I C omega. The expression for the response exam that is complex, meaning that there is a phase difference, but basically means there is a delay in time between the force and when the object is really feeling the force, no? Okay, or the velocity, so phase difference between, so there is a lag in time between the excitation f of t and the displacement or response. I use displacement not to repeat response, but you could use response if you want. X of t. So I call it here phase difference, but if you want, you can say a lag in time between when you apply the force and the deformation, no? Okay? So that's the important part over here.